Okay, so we've got some more here. Again, if you were going to do the derivative of something like the cube root of x, you wouldn't do it in that form. You would rewrite it into a power function, right? Same thing here for integration. We'll want to think about these things as power functions. So this is going to be the integral of 6x to the 1/3 power dx, right? You would think about it as its power function first, and then did you get a note packet when you came in? Because we got more note packets up here. Looks like Young needs one. Anyone else miss one when they came in? You got one. No. I just noticed that he didn't have his note. Neil came in after I started, so they didn't get the note packets. Okay. It's easier to follow along, because that's something to follow along with, right? Okay. So, rewriting our radical as a power function. And then we know the constant multiple, so it's going to stay a constant multiple, so leave your 6 alone. What do you do to your x to the 1/3 power? It becomes x to the 4/3, and you're adding 1. Okay? So x to the 4/3. It's really awkward to write divided by 4/3, so instead of writing divided by 4/3, you multiply with the reciprocal, because you're dividing by a fraction, right? So times 3/4 plus c. So if I reduce that, that will be 3 times 3 is 9/2. X to the 4/3. Sound good? Just reducing my multiplication there, 3 times 3 and 1 times 2. Again, I was supposed to divide by 4/3, but who divides by fractions by writing divided by 4/3? You multiply with the reciprocal instead, and we're good. Okay. If you had to do the derivative of this, what would you do? Probably do first. Distribute it, right? So I would want to distribute this. I want to definitely distribute this for the integral. Okay? So I don't get to do integrals piece by piece over multiplication. I do get to do them piece by piece over addition. This is the same thing as the integral of 60m to the 4th minus 50m squared dm. And then I know I can do both parts of addition or subtraction separately, so we'll go ahead and do those separately. So I have 60m to the 4 plus 1 is 5 divided by the new power of 5 minus 50m to the 3rd over 3 plus c. And then simplify, we got to simplify at least the 60 and the 5, because those reduce down to 12. M to the 5th minus, it looks a little weird if you don't put your numbers together, so make it 50/3. M to the 3rd plus c, just because the numbers should go together, right? Now, sometimes I might just do that, so instead of writing it says 50 m to the 3rd over 3, I would make it 50/3 to start with, right? Because I'm dividing by 3. It doesn't really matter where I divide by 3, but we'll get more practice writing those things down as we continue. Okay. Similarly, in part C, I am able to split an integral into 2 parts if I have an addition or subtraction, not for multiplication and not for a division. So I really have no choice but to distribute my division first, right? So I have to do the integral of distributing the division, t to the 8th divided by t to the 3rd is t to the 5th. So 12t to the 5th minus t to the negative 2 dt. If I reduce that, there's no point writing it as 1 over t squared because I don't have a rule for that. I have a power rule instead, so write it in power form. Okay. Then you can do both parts of the sum. So that's going to be 12 t to the 6th over 6, right? Adding 1 to the power, putting my 6 under the 12 so I can divide the numbers, minus t to the negative 3 divided by t to the negative 1. I accidentally did a derivative. It's going to happen sometimes to you guys too. You're so used to your derivatives, right, by subtracting 1. I'm supposed to add 1 there. I get negative 1. So divided by negative 1. Yeah, it does happen. You got antiderivatives and derivatives, and there are some problems you have to do a derivative then an antiderivative. So you really have to try to focus on what you're doing. Antiderivative, so I'm adding negative 2 plus 1 is negative 1.
When doing derivative, then antiderivative, just put you where you were.
Oh, yeah, well, if you were going to do a derivative, then an antiderivative right away puts you where you are, but sometimes you'll have
Or
to,
like a second derivative, then-
so we'll get there. Yeah, but sometimes you do a partial, like a derivative, just part of the function, and the antiderivative of the whole thing. It's part of U substitution, but we'll get there. That's section 5.5. Okay? We will get there. But you do have to be really careful then, because remember, when am I actually doing a derivative? When am I decreasing my power? When am I actually increasing it for antiderivative? So I definitely need to rewrite this because it's super messy. So I've got 2, t to the 6th, negative, negative, so plus t to the negative 1. I don't need to write the 1 in the denominator. So then plus c. So there we go.
Exactly sure in the beginning. How did you change that to 12 t to 6?
Okay. So the first thing I was thinking was distributing the division so that each part of the numerator got divided by the denominator. So we distributed the division. And then reducing our t's gave us the t to the 5th right there. And reducing our t's here, if I use like the 1 minus 3 is negative 2, I can get right to the negative 2. Or you could think about that as 1 over t squared first, and then go to t to negative 2, whichever one makes you more comfortable.
Okay.
Yep.
That makes a lot more sense. Now.
Yeah.
Thank you.
Yep. So again, we can write the extra step to distribute, but we were distributing our division. We can distribute monomial. It's because the denominator was monomial, right? Monomial multiplication distributes, and so does monomial division. Yep. All right. Of course, if you distribute binomials, you can still do it. It's just more complicated, right? You can distribute a binomial multiplication. You can distribute a binomial division. They're just both more complicated. Monomials are one little distribute each. Okay, so we're going to flip our page. Let's see what else we got. Okay, so now we have just some more rules. The non-power function. We've got the trig functions. So the integrals of each of the following. Okay, so first of all, the antiderivative of sine of x. Okay, which function has sine of x as its derivative? The derivative of cosine is negative sine, right? So that means that the antiderivative of sine has to be negative cosine. That way, when you do the derivative of cosine, you have negative negative to make that sign positive. Okay? All right. What about if you want to do the antiderivative of a sine of 3x? So it would be negative cosine of 3x's derivative would be times 3. So we have to do divided by 3, right? It's the opposite of the chain rule on that part, right? So negative cosine of 3x divided by 3 would have sine of 3x as its derivative. Okay? And so what if we had sine of ax, where a is any real number, same kind of idea with this 3, it would be negative cosine of ax divided by a, right? Because the derivative of negative cosine of ax would be negative, negative, sine of ax times a, and the two a's would cancel, two negatives would cancel back to the sine of ax. Okay? All right, so in the table below, we can just, again, get some general properties here. We know the derivative of sine of ax. This is built for the chain rule on that, so it gives you a times cosine of ax for the derivative, right? So built for the chain rule, again, the derivative of cosine of ax will be 1 over a sine ax plus c, okay? So we have like these two go back and forth. One's a derivative, one's an antiderivative. The one we were just working with was the antiderivative of sine of x, negative 1 over a cosine of ax. We just did that one off on the page above. So thinking about this, the derivative of sine is positive cosine. The antiderivative of sine is negative cosine. The derivative of cosine is negative sine. The antiderivative of cosine is positive sine. So you might even want to think about them across too, like as which one's positive, which one's negative. We have our negatives for, oops, not negative there. Negatives for opposite functions. There's no negative on those two, right? So that one's positive. we have our negatives for the derivative sign is positive, the antiderivative is negative, the derivative cosine is negative, the antiderivative cosine is positive. Okay. Then I can't do the derivative or the antiderivative of tangent or secant as easily, but I can do the derivative of secant squared and cosecant squared because those had direct derivatives from tangent and cotangent. So I can do the antiderivative of cosine and sine, secant squared, cosecant squared, and I can also do the derivative of the product of secant times tangent and cosecant times tangent, because remember the derivative of secant was secant tangent. So you had a product of secant tangent and a product of cosecant cotangent. Those two I could do. Okay? So we have to be a little more thoughtful about our trig functions because their derivatives were sometimes a different function than you started with, or a different kind of function than you started with. And I took one function and got a product for its derivative. So I need a product now that I can differentiate or integrate back to one function for the trig functions. Okay. All right. Next page.